In this video for chapter 17, we're going to walk through how to do calculations for titrations. So in the previous video, we walked through what titration curves look like, and I emphasized the fact that they are best viewed as a graphical representation of a process. So in this video, we're going to go through the steps and look at how we can calculate pH along various points in that process. Okay, and the best way to go through that is to just work a nice long example with several different steps along the way. So we're going to start by finding the pH of 25 milliliters of 0.5 molar weak acid. And we're going to say that the pKa for that weak acid is 7.2, and the Ka for that weak acid 6.31 times 10 to the minus 8. Okay, so right away we can take notice of the fact that our concentration is much, much larger than our Ka. Okay, so when we do this first step, we can assume that X is small. We can simplify our math. All right, so we're just dealing with a generic acid. So I'm going to write the generic acid equation, HA plus H2O gives us H3O plus A minus. Right? So we're starting with 0.5 molar weak acid. And at this stage, where all I'm doing is calculating the pH of my acid solution, I don't need to worry about the volume. That will come into play when we start adding some base in our titration. So I can start with my 0.5 molar, none of this and none of this. You say minus X, plus X, and plus X. And we assume that X is small, so I'm just going to have my E line looking like this. Right, so I'm going to write my Ka expression, and that will allow me to solve for X because I want to know the pH. So that comes from right here. Okay, so Ka is X squared over 0.5 minus X, and remember we're going to say that X is small. That will simplify our math immensely. Equals our Ka, 6.31 times 10 to the minus 8. We'll do the math and we'll find that the pH is 3.8. Okay, so hopefully at this point in time, solving for X in this type of equation is relatively second nature for you all. Okay, so if all I have is my 0.5 molar solution of weak acid, the pH is going to be 3.8. So let's take a look as we start our titration. So first step, we're going to take a look at find the pH with 10 milliliters of 0.5 molar NaOH added. Okay, so the NaOH is in the burette. My solution of weak acid is in the Erlenmeyer flask. And now we've added 10 mils of sodium hydroxide, and we're going to see what the pH is at this point in the titration. Okay, so first we need total moles of acid. Right, and we need moles in this case, as opposed to when we're just doing the pH of the weak acid by itself. When we have started our titration, everything about titrations is a mole-to-mole interaction. So I need to know moles of acid, and I need to know moles of base added. Right, so we have 25 milliliters of 0.5 molar acid. And I can simplify my math a little bit by saying millimoles per milliliter. Okay, you can always use those equivalents if I want to do kilomoles per kiloliter or anything like that. As long as I do the same thing to both, I don't have to change my units. Right? So we have 12.5 millimoles of acid. Okay? I also need moles of base added. Right? And we've added 10 milliliters of 0.5 molar NaOH. Should be millimoles. So I've got 5 millimoles of base added. Okay, so now I'm going to make an ice table, because we always have to make ice tables when we're dealing with weak acids. And we're going to start with some quantity of base. HA plus OH gives me A minus plus H2O. Okay, I'm interacting my weak acid with my strong base. Right, so we're starting with 12.5 millimoles here, 5 millimoles here. Okay, so just looking at buffer capacity and things of that nature, if I start with less base than I have acid, my acid's just going to neutralize the quantity of base that's there. So I've got 5 millimoles of base, 12.5 millimoles of acid, so all of my base is going to get removed. Okay, so at my equilibrium line, I'll have 7.5 millimoles of acid left, no base left, and now I have 5 millimoles of conjugate base. Right, so now I have a buffer. I've got some acid and its conjugate base in the same solution together. So, Henderson-Hasselbalch. So now that I know the equilibrium values for the acid and the conjugate base, I can plug those into the Henderson-Hasselbalch equation. Log of the base over the acid, so log of 5 over 7.5. So at this point in my titration, my pH is now 7.02. All right, it was, 3.8? Right, and just with the addition of 10 milliliters of acid, my pH is now 7.2. Right, so pretty big jump there. Right, let's see what happens when we add a little more base. Right, let's say 12.5 milliliters. Right, so now we're going to keep doing our ice table. A minus. Right, so we still keep that same amount of acid that we started with. And now we have 6.25 millimoles of base added. None of this and none of this to start. I still have more acid than base, so the base is just going to get neutralized. Right, so in my equilibrium line, I'll have 6.25 millimoles of acid left, no base left, and now 6.25 millimoles of conjugate base. Right? So again, I've got some acid and its conjugate base, nothing else, so Henderson-Hasselbalch again. Log of the base over the acid. Okay, so take a look at where we are. So remember in the previous video we talked about a thing called the half equivalence point. And the half equivalence point was where moles of acid equals moles of conjugate base. And at the half equivalence point, pH equals pKa. Right? So at this point in the titration, we are at the half equivalence point. Because my moles of acid equal my moles of conjugate base. Now let's see what happens when we go past our half equivalence point. Let's see if we actually exceed all of that and get to the equivalence point. Okay, so at the equivalence point, moles of acid equal moles of base added. Okay, so I've got 12 millimoles of acid, so at 12 millimoles of base added, that's going to be at 25 milliliters. Okay, so let's take a look at what happens there. So we actually will have one extra step when we get to the equivalence point. So we've got our acid, we've got our base, conjugate acid, and some water. So we're going to, our moles of acid equal our moles of base, so we go to minus 12.5 for each. So we'll have 0, 0, and 12.5 millimoles of conjugate base left over. Okay, this is very important. So now, we're actually at a very similar place to where we were at the very beginning of this demonstration. So remember, the first thing that we did was we figured out what was the pH of a solution of weak acid by itself. So now we're in a situation where we're going to find the pH of a weak acid, or excuse me, the conjugate base by itself. Sorry, my handwriting is wonderful for this video. Okay, so we treat it exactly the same way. So in this case, we do want to use concentration, right? So right now we have 12.5 millimoles of A minus. Okay, and our total volume Remember, we started with 25 milliliters of acid. And now we've added 25 milliliters of base. Right, so our total volume is going to equal 50 milliliters. So we need the concentration of our weak base. So we've got our 12.5 millimole of A minus and our 50 milliliter total volume. So 12.5 millimoles divided by 50 milliliters gives us a molarity of 0.250. Okay, so remember it's moles per liter or millimoles per milliliter. Really doesn't matter as long as I do the same thing to both. So 0.25 molar A minus. Okay, we also need Kb. In order to find the pH of a weak base, we need to know Kb so that we can solve for X that way. So Kb is 1 times 10 to the minus 14 over Ka. And our Ka was 7.2 times 10 to the minus 4. So our Kb should come out to be 1.4 times 10 to the minus 11. Right, so once again, I want to point out our concentration and our K value are very, very different. So we're going to be able to assume that X is small. Right, so we're going to approach this the same way that we did with solving the pH of the weak acid by itself, but we're going to start with a base ionization equation. All right, so we start with our 0.25 molar. And we say minus X, which we'll assume that is small, X and X. All right, so our Kb expression will be X squared over 0.25 equals 1.4 times 10 to the minus 11. So X squared equals 3.5 times 10 to the minus 12. So X is 1.9 times 10 to the minus 6, which equals our OH minus. Okay, we find that right here. Right, so I need to find POH. From that, POH is 5.72, which means that our pH is 8.27. Okay, a little bit of rounding there. I realize that those two numbers don't add up exactly to 14 as they're written there, but there is some rounding. So once we hit the equivalence point, notice that we are in the basic range. Right? And the reason for that is that once I've neutralized all my acid, what I'm left with is some conjugate base. So I should have a slightly basic pH at the equivalence point. So when we titrate a weak acid, the equivalence point will be basic. Okay, and when we titrate a weak base, the equivalence point will be acidic. Right? And when we titrate a strong acid or a strong base with a strong acid or a strong base, when it's strong on strong, our pH will be close to 7, if not exactly 7. Okay? So this is an important thing. So when we do these titration calculations, we need to be in moles, and we need to figure out if we have exceeded the capacity of the buffer. Okay, so in our last example here with adding enough base to completely neutralize our acid, which is what we did here, we're left with some conjugate base left over. Right? If we were to titrate a weak base with a strong acid to the same point, we would be left with some conjugate acid left over. Right? And when we have that situation where there's no acid left and we're left with some conjugate base, then we have to react it with water, one more step, do one more ice table in order to figure out what the final pH will be. Right, now the last thing that I want to talk about actually kind of should have been in the previous video because it pertains to titration curves, but it is the topic of polyprotic titration curves. Okay, so what those look like, they have a similar form, but they are multi-step. Right, so we're going to titrate sulfuric acid with NaOH. Okay, notice that sulfuric acid has 2 protons. Okay, and they're both acidic protons. So when polyprotic acids come apart, they come apart one step at a time. Okay, so what our titration curve is going to look like, first off, this is a strong acid. Sulfuric acid is one of our strongs. So our first proton is going to have a similar titration profile to a strong acid. But once we hit that, our second proton is not for a strong acid. Now I've got HSO4 minus, which is a weak acid. So after we've neutralized that first proton, we get the typical buffer ramp. And then we'll get a final equivalence point, and things will level off. All right, so our first equivalence point is right here. And then we have a buffer region, which is a half equivalence point. And we have a second equivalence point. All right, now just like when we do a weak, we have a buffer region. All right, where pH equals pKa for the weak acid, for HSO4 minus. Okay, so let's take a look at some equations to sort of illustrate this. So we start with our strong acid H2SO4. We write an ionization equation for it. It's a strong acid, so it only comes apart. Right? But now what we have is a weak acid in water. So we need to address that. So we'll have HSO4 minus plus H2O. We have a double-headed arrow because it's a weak acid. Makes SO4 2 minus plus H3O plus. And this is our buffer. Okay, so this will correspond to our first equivalence point. Right, so our first equivalence point is neutralizing this first proton. And our second equivalence point is neutralizing the second proton. And in between, we have our weak acid HSO4 minus, which is where we get the ramp of the buffer region. Okay, so that's going to do it for this video. On our next video, we're going to leave acids and bases and start talking about solubility.